So let us start with the transportation problem. What is a transportation problem? Suppose you are given M sources and N destination, and you want to transport a homogeneous product, means one product you want to transport, say apples, from these sources to the destinations. And suppose AI is the amount of the product available at each destination, say ith destination or ith source, and Bj is the requirement of the same product at the jth destination. And suppose Cij is the cost associated with transporting this product from ith source to jth destination. So it is the unit cost of transporting the product, means if you are transporting 1 unit of the product, the cost will be Cij, okay, from ith source to jth destination. Then our objective is to construct a transportation schedule, okay, that transport my products from sources to destination in such a way that my overall cost of transportation is minimum, and keeping in mind that the supply limits at sources and destination must be exactly satisfied, that the amount available at sources must be supplied to the amount available at destination. So that means the total amount available at sources should be equal to the total amount required at the destination. So from I equal to 1, because you have M sources and N destination. So this will be one additional assumption will be um, taking care. Okay, let me explain the construction of this problem from 2 sources and 3 destination. Okay. So example with uh, say 2 sources and say 3 destinations. Okay, suppose I have the sources as this, and I have 3 destinations, 1 and 3 destinations. Okay, so suppose this is my source 1, source 2, and this is my destination 1, destination 2, and destination 3. Okay, and suppose from source 1 to destination 1 I can supply, so I have a route from source 1 to destination 1, and suppose the availability of the product at source 1 is say A1, and the availability of the product at source 2 is A2. Similarly, requirement of the product at destination 1 is B1, here we have B2, here we have B3. Okay, now we want to construct a transportation schedule so that will transport the product from each source to destination in such a way that overall cost is minimum. So we can see that from source 1 to destination 1, we can transport. Similarly, from source 1 to destination 2, there is a possibility of transportation, and from here to here, it is a possibility of transportation. Okay, and the cost of transportation from source 1 to destination 1 is say C11, because I have written that Cij is the cost of transportation from ith source to jth destination. So from first source to first destination, the cost is C11. Similarly, C12, C13. Now the question is how much I am transporting from each source to each destination. That is the question, so that my overall cost of transportation is minimum. Looking at the structure, we can see there are a number of routes available that allow me to transport from each source to each destination, but we have to select very carefully so that my cost is minimum. So what we do not know here in this case is how much amount I am transporting from my sources to the destinations. So my variables are clearly what? So my variables are Xij. Okay, so Xij is what? It is equal to the number of units of the product transported from ith source to jth destination. Okay, so that means if I am transporting from source 1 to destination 1, say x11 number of units, and from source 1 to destination 2 I am transporting x12 number of units, Similarly, x13 number of units. Similarly, I have options from source 2 to all these three destinations. So I can say I will transport say x21 units from here, x22 from here, and x23 from here, and the cost associated with them is c21, c22, c23. The cost of transporting one unit from sources to destination one is C11, but I am transporting X11 units from source one to destination one because X11 is my variable. X11 says the number of units transported from source one to destination one, which I would like to determine at a later stage. But as of now, I do not know, so they are the variables. So according to these variables, what will be my cost? So the cost will be my C11 X11. Similarly, if I am transporting X12 units from source 1 to destination 2, my total cost of transportation will be, for 1 unit my cost is C12, for X12 units my cost of transportation will be what? C12 X12. Similarly, for X13 units my cost of transportation is C13 X13. Similarly, C21 X21 plus C22 X22 plus C23 X23. So this is my overall cost of transportation, and I want to minimize this cost of transportation. Okay, so my objective is to minimize this cost of transportation. Okay, but then what are my constraints? My constraint is that availability and requirement must be exactly satisfied. Okay, so since I have A1 units available at source 1, so how A1 units are distributed? So A1 units can be out of A1, X11 units are distributed to destination 1, X12 to destination 2, and X13 to destination 3. So that means X11 plus X12 plus X13, that must be equal to A1. Similarly, for second source constraint, how much I am transporting from here is that X21 units from source 2 to destination 1, X22 units, and X23 from source 2 to destination 3. So the total of these units are equal to what? A2, because A2 number of units are available at source 2, which are being distributed to all these three destinations. Okay. So similarly, these are my source constraints. Similarly, I am having my destination constraints. So I see at destination 1, I am receiving X11 units from source 1 and X21 units from source 2. So X11 plus X21 I am receiving from these two sources, but this must be equal to what? The requirement of the destination 1, which is equal to B1. Similarly, at destination 2, how much I am getting? X12 plus X22, this is equal to P2. And for destination 3 is X13 plus X23 is equal to P3. And number of units are always non-negative. So my Xij is greater than or equal to 0 for I equal to 1 to 2 and j equal to 1, 2, and 3. So this is what I call my transportation problem, the mathematical model of my transportation problem. Okay, so you can see that from this model that the objective function is linear, okay, and the constraints are also linear because there is no higher degree variable is available. So you can see when the objective function and constraints are all linear, we can see that this is a linear programming problem. So my transportation problem is a linear programming problem. And we know that the linear programming problem can be solved by simplex method. Now I will be discussing why I'm not using the simplex method directly to solve this problem. What are the limitations for the simplex method and why I need to relook at the theory of the linear programming problem and to devise a new method. Okay, so before I proceed further, let me write the mathematical model when I have my m sources and n destinations. So in case of m sources and n destinations, you can see my model becomes minimize summation Cij Xij, I goes from 1 to m, j goes from 1 to n because I'm taking sum over all I and j here. So if you look at these source constraints, that for first source A1, my first index is fixed and the second index is varied over the constraint. So that means it is xij equal to ai for each I equal to 1 to m, and the summation is taken over j. So for each I, for I equal to 1, you can see my first index is fixed, and for all the uh, um, destinations, I'm taking the summation. So for first source, from first source to all destination, I'm supplying the A1 unit. Okay. Similarly, this there are m equations for each I am having the same inequality. And similarly, for the destination constraint, I have xij is equal to bj for each j equal to 1 to n, and here the summation is taken over I equal to 1 to n. Okay, and my xij are greater than or equal to 0. So this is my mathematical model for a general transportation problem where I have m sources and n destination. This is my transportation model. Okay, so before I start discussing the theory behind the solution of this transportation problem, which is again a linear programming problem, let me have a look at some of the properties of this problem. Okay, firstly, because transportation problem is a linear programming problem. Okay, so if it is a linear programming problem, we see that every linear programming problem we can write in this form: minimize C transpose X subject to ax equal to b, x greater than or equal to 0. Now, can we put the same problem in this form? So we need to identify the C matrix, A matrix, and the B matrix. So I will explain this thing for my 2 source and 3 destination case. Okay. So from here, you see my A matrix is what? You can see in case of 2 source and 3 destination problem, I have minimize what C11 x1, C12 x11 x12 up to C23 x23 subject to the constraints x11 plus x12 plus x13 is equal to A1, x21 plus 22 plus 23 is equal to A2. Similarly, x11 plus x21 equal to B1. Similarly, x12 plus 22 equal to B2. And for third destination, I am supplying from source 1 to destination 3 and source 2 to destination 3 equal to B3, and xij is greater than or equal to 0. Okay, now you look at the matrix here. So these 2 constraints are my source constraints. And these 3 constraints are my destination constraints. Okay, so then my A matrix here becomes what? You see, my variables are what? x11, x12, x13, x21, x22, x23. Okay, so corresponding to each variable, I will write the coefficients from the equations here. So I see it is 1, 0, 1, 0, 0. For x12 is 1, 0, then again 0, 1, 0, because in first constraint there is no x12, but in second constraint we have x12, so we will put 1 here because coefficient is 1. Similarly, for x13 is 1, 0, 0, 0, 1. In the third constraint I have x13. Similarly, for x21 I have 1. X21 is not in the first constraint, so it is 0, 1, 1, 0, 0. Similarly, for x22, I have what? 0, 1, 0, 1, 0. And for x23 is 0, 1, 0, 0, 1. Okay, so this is my A matrix. And what are my variables? X1, X2, X3. And what is my right hand side matrix here is what? This is my A1, A2, B1, B2, B3. Okay. And my cost matrix C is what? C11, C12. My cost matrix C is what? C11, C12, C13, C21, C22, C23 transpose, because all the vectors are column vectors. Okay. So this is my A matrix. Now the next question is that since the transportation problem is my linear programming problem, so we know that the optimal solution of an LPP, if it exists, is attained at a basic feasible solution. Okay, so that means the optimal solution of my transportation problem will also occur at a basic feasible solution. So we must identify the basis for this problem first. But if you look at the A matrix here, you see you do not have any identity matrix here in this case, right? And if you want to solve this problem by using say a linear programming problem or the simplex method, firstly I will need to create an artificial identity. So I will add 5 artificial variables, and then I will apply at least 5 iterations to get initial basic feasible solutions. Okay. Moreover, there are a lot of zeros and ones, so the problem, the matrix is really very sparse. Okay. But I want to tell you that the number of variables chosen in the basis is equal to the rank of the matrix. That we know that the number of variables in the basis is equal to what? It is equal to the rank of the matrix A. So firstly, we will find the rank of the matrix A. So if I say that there are 5 variables in the basis, then rank of A must be 5. But I will tell you that the rank of A is not 5. So you simply observe that if I change my row 1 to what? Row 1 plus row 2. Okay. And I change my row 3 to what? Row 3 plus row 4 plus row 5. So you will see what I am getting after applying these operations. I will be getting what? 1, 1, 1, 1, 1, 1. Okay. And second row is 0, 0, 0, 1, 1, 1. And since in the row 3, I am adding row 3, 4, and 5. Row 3, 4, and 5. Okay. So it will become what? It is 1, 1, 1, 1, 1, 1, then 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1. Okay. Now you see these two rows are identical. So next, if I apply in this reduced matrix that row 1 minus row 3, I change my first row as row 1 minus row 3. So you will see one of my row will become completely 0. So that means this matrix has rank less than or equal to, in fact, less than 5. Why? Because one of the row is equal to 0. So every minor of order 5 in this matrix has determinant 0. So the rank of matrix is not 5. That means 5 variables cannot be in the basis. Okay. So the rank of the matrix is, so that means rank of A is not equal to 5. Rather, rank is equal to 4. Okay. So why rank is 4? That I will leave as a homework to observe that you can find one minor of order 4 whose determinant is non-zero. Okay. So observe this thing. So rank of, so if you have m sources, so in this case you had 2 sources and 3 destinations. So 2 sources and 3 destinations. Okay. then rank is equal to what? It is 2 plus 3 minus 1 is equal to 4. Okay, so rank of the matrix is 1 less than the sum of the number of rows and the number of source rows and the number of destination rows. Okay, so if I am having next, if we have m sources and n destinations, then rank is what? Then
You
rank
can
is
just throw the
m
distribution and
plus n minus 1. Okay, so if we have m sources and n destination, the rank is what? Number of rows corresponding to the source rows plus corresponding rows corresponding to the destination rows, m plus n minus 1. So it is sum total of sources plus destinations minus 1. So rank is m plus n minus 1. That means exactly in this case 5 variables cannot be in the basis, but in the basis we have one variable less because one of the row is redundant and it can be made 0 by using elementary row operation. So next task is which of the m plus n minus 1 variables to be chosen into the basis, chosen for basis. Okay, I would like you to observe here again that in this case, in this case, in my A matrix, in the variables, suppose in the A matrix, the columns corresponding to my variables x11, x12, x13 are what? A11, A12, A13, say A21, A22, A23. So these are my column vectors. So I have a simple observation here. In check that A11 minus A12 plus A22 minus A21 is equal to what? So again, if I draw my A matrix here, I can see, just for the reference I am writing here, this is my A matrix in case of transportation problem. These are my columns A21, A22 and A23. So if I add A11 minus A12, so what I am getting here is, see, write the column of A11, 1, 0, 1, 0, 0 minus, what is the column for A12? A12 is 1, 0, 0, 1, 0 plus the column of A22. The column of A22 is 0, 1, 0, 1, 0 minus A21. A21 is 0, 1, 1, 0, 0. Okay, you see from here that 1 minus 1 is 0 plus 0 minus 0. My first component is 0. What about the second component? 0 minus 0 is 0 plus 1 minus 1 is again 0. For third component, 1 minus 0 plus 0 minus 1. So it is 1 minus 1 is again 0. For fourth component, if I check, 0 minus 1 plus 1 minus 0. So minus 1 plus 1 is 0 and rest of the components are again 0 is 0. So for last component, we have all the zeros. So this is 0. So what we have seen that A11 minus A12 plus A22 minus this is a 0 vector. So what information does it give? Okay, so it tells me that these components, that my variables x11, x12, x22 and x21, these four variables are linearly dependent. So if these variables are linearly dependent, so that means these four variables, so they cannot be in the basis together. So that means it is possible to observe from this A matrix that which of the variables are linearly dependent or independent. So I will not talk about the independent variables, but clearly it is possible to look at the variables, that which of the variables are linearly dependent, that their linear combination is giving me 0. So non-negative linear combination is giving 0 in case of A11, A12, A22, A21. So these four variables are linearly dependent, so they cannot form a basis. Okay. But then since we have six variables, and out of six variables we have to choose four variables in the basis. Why four variables in the basis? Because rank of my matrix is 4. So which of the four variables I will choose in the basis? But I have figured out that which four should not be in the basis. But then this is again a difficult procedure in case like we discussed here, that how many combinations we can check for the linear dependence. So this is not a advisable idea. But alternatively, if I look at this problem from another point of view, so please observe here that I put this problem in tabular form. So what is my tabular form for 2 cross 3 case? So I see I have my two sources and three destinations. So this is my source 1, source 2. This is my destination 1, destination 2, destination 3. Okay. From the first box is actually representing my variable x11. So I can say it represents my uh, my vector a11. So I can say this or it represents my cost vector c11. So if I say c11 is the cost of transportation from source 1 to destination 1, c12 here, c13 here, c21, c22, c23 here, and the availability at source 1 is a1, at source 2 is a2, and requirement of destination is b1, b2, b3. Okay. So now you see, in order to have four variables in the basis, like I have initially chosen in this case, we see I tried to take x11, x12, x22, and x21 into the basis. So that means these are four boxes which represents my variables x11, x12, because if I'm transporting x11 units, so that I will put here that x11 is the number of units I'm transporting from source 1 to destination 1. Okay. So from x12 I'm transporting here. Okay. For x22 I'm transporting here, and x21 I'm transporting here. So these are the four boxes I'm considering here. And you see these four boxes are actually making a closed loop type structure if I draw horizontal and vertical lines. Okay, so this is one observation that I'm having in the transportation problem, that if I'm taking four variables into the basis, and if they are making a closed loop type structure while I draw horizontal and vertical lines, so these four variables cannot be in the basis. So whenever there is a loop kind structure, so these variables are not in the basis. Okay. So similarly, I can look for another choice. Say for instance here, if I take my variables so take my variables as say x11, x13, x21, and x23. So x21 and 23. So now these four variables are what? They represent corresponding to these boxes. Again, if I draw horizontal and vertical lines, I see they make a closed loop type structure. So that means this will also not a choice for a basic feasible solution. Why? Because they are forming a closed loop type structure, and the columns of these four variables in the A matrix, they will be also what? They will be linearly dependent. Okay. So then the question is, which of the variables should be taken into the basis? That means the variables. So I have to choose those 4 variables which do not form a closed loop type structure. Okay. So that means, so observation again. So in case of 2 sources, 3 destination problem. So what we have to do, we have to choose choose 4 variables in such a way that they do not form a closed loop in the cost matrix. So this is what I call the cost matrix. Okay, and as an example, I can say in this case for 2 sources and 3 destination. So I can have 1, 2, 3, and 4. These variables, if I draw, so there is no closed loop type structure. So it starts from here and ends at the 4th one. So this can be a valid choice for the basic feasible solution. So this implies that my x11, x12, x22, and x23. x11, x12, x22, and x23. So they form a basic feasible solution. So what we have discussed today is that in order to find a basic feasible solution for a transportation problem, in particularly we considered the case for 2 source and 3 destination problem, that we have to look for m plus n minus 1 variables. And secondly, these variables do not form a closed loop. So this is the main point which we understood in case of a transportation problem to find a feasible basic solution for this problem. Okay, so m plus n minus 1 condition determines that the number of basic variables are equal to the rank of the matrix, and this closed loop type structure, if they do not form a closed loop type structure, it also ensures that the variables we are choosing are not linearly dependent, they are linearly independent. Okay, so I will stop over